Isn't that a sexy model? Wouldn't you like to know how to make your own? Well, stay tuned and you can. So the first question to answer is, why do a parametric model? Well, the short answer is that it allows you to make changes easily. And if you want something like a scale model that you can adapt to a variety of different builds, then that is a very useful feature. So for example, with this particular project, even though I created the model, you'll be able to take it and modify it and make it your own according to what you have. Whenever you're doing a scale modeling project, you want to adjust according to a few simple parameters. So the main thing you want to look at is what is fixed in your project and what you can change or modify easily, or at least get close to the required dimensions. In most cases with a scale model, you're going to be looking at the body tube. So this would have a fixed dimension, both outer and inner. For this example, we're going to be using the Apogee rocket's 29mm body tube. And there are a number of reasons why you might decide on which tube you want to use. In my case, the reason I picked this one is because I have some. Okay, so with that body tube now selected, we're able to modify the fin can and the nose cone to match the same scale. So based on the dimensions of the body tube, we calculate our scale, then adjust all those dimensions accordingly. Now for this project, all the dimensions are going to be based on this diagram created by G. Harry Stine, founder of the National Association of Rocketry and former president. Also the author of the Handbook of Model Rocketry, which is where I first came across this particular drawing. It is available online in a variety of places. Just Google Nike Smoke dimensions and you'll be able to find it. I'm not linking to it here because I don't have permission from the copyright owners, but it is widely available on the net. Okay, so if you're going to create this model yourself, you're going to start by importing the model. In Fusion 360, you would go to the File menu, select Upload, select the file you're going to upload. In this case, it's the Nike Smoke Fusion 360 diagram. Select the location where you're going to place it, and then upload. Since I've already got it here, I'm not going to hit the upload button. I'm going to work with the version I have. Okay. So let's look at what we need to do. Again, as I've mentioned, we're going to be basing all of our dimensions off of the dimensions of the body tube. So we need to be able to set that. We have a number of configuration parameters, and they're all available if you go into the Modify menu and then select Change Parameters. It'll show you the parameters we have. Okay, so I'm going to close the favorites here, and you can see we have all kinds of user-defined parameters. Now, unfortunately, Fusion 360 doesn't allow me to put these in an order that makes sense. So what I've done is in the favorites, I've put all the ones that you might want to modify, and any others are going to go below. They're basically added in whatever order you create them. So that's the reason for this particular order. It may look kind of random, and to some degree it is. But the two key parameters we're going to look at are the inner and the outer. Now, I've looked up these dimensions for the 29mm body tube from the Apogee Components website. And I've specified this in inches because the rocket that we're doing the model of is an American rocket, and the drawing is in inches. That's a fact of life when doing scale modeling, so unfortunately those of us used to millimeters have to deal with that. But Apogee is pretty accommodating. Being an American site, they do give their dimensions in inches. Now the scale itself is based on the outer diameter. Okay. Now I have some other parameters below, and I'm just going to duck down here to look at it. One of which is, this is a fixed parameter, the Nike diameter. So this is the diameter of the actual rocket according to the diagram. So it's 16.5 inches. We can then calculate the scale. So it's the Nike diameter, 16.5 inches, divided by our outer diameter, 1.176 inches. And the times 1 inch just means that we want to specify this measurement in inches the default being millimeters internally. Okay, so this is going to produce a 1/14th scale model. Now we can change this, and I'll show you an example of that later, and it will adjust that scale. Okay. There are some other parameters that fall out of this too. So for example, the body length. This specifies the length of the body tube we require. So we're going to have to get out our ruler and our body tube and our X-Acto knife and cut it to this length. Okay. So that is really one of the critical driven dimensions from this that it is going to calculate for us. Okay. So we'll come back to these in a moment, and let's look at the other input parameters. And again, they are a little bit out of order because of just the way Fusion does things. So I'm going to look at the wall and the fin can. So the wall is the thickness of the nose cone. Okay, so the trade-off is thicker is more robust, but it's also more weight. And thinner is more likely to be damaged, but again, less weight. Now in this particular case, it's a fairly small model and the weight is not significant. 2 millimeters is a good trade-off between strength and weight. And remember, you can also use this to some degree to adjust the center of gravity of your rocket as well by moving some of the weight forward. The fin can, this is a little thinner than the nose cone for a couple of reasons. One of which is, even though the diagram doesn't specify the thickness for the fin can, it is pretty thin. It is a metal fin can, and it has the additional structure of the body tube itself to give it strength. So it doesn't need to be as thick. There is kind of a minimum you're going to get away with here simply because of 3D printing process. So 1 millimeter isn't a bad choice. There are some fit parameters. Okay, so we have inner fit and outer fit. So since we're here, let's look at the outer fit. So this is a adjustment for objects that go on the outside of the body tube. So on the fin can, for example, this needs to be a little bit loose so that we have the ability to slide it onto the body tube, as well as attach it with CA glue, cyanoacrylate. And I use a medium glue for this because it does fill that a little bit and gives you a nice strong bond. So that's the outer fit. This one is reasonably big. It's 0.5 millimeters, which means it's 1 millimeter in diameter. And it doesn't sound like a lot, but it really does make a difference for sliding that fin can over the body tube. The other one, the inner fit, the only place that that's actually affecting is the nose cone. So let's highlight that, the nose. Yeah, it's not going to highlight it. But basically there is a, well, let's get rid of the body tube here. Yeah, so there is a portion that goes inside the body tube, and that's what holds the nose cone in place. You want that to be a reasonably tight fit because as the rocket is flying, that's what's holding the two pieces together. It is not glued in place, so you want that snug. And in this case, I've specified a very small fit parameter to this, and you might even want to go a bit lower. You can adjust that after the fact a little bit with some masking tape or whatever to shim it into the correct dimension. But if you make it a little bit oversized, too big for your body tube, you can also sand it down a little. So this can even be as close to 0 as you want to make it. The other two parameters are the nose attach width and height, and that describe this post going across at the base of the nose cone. Now, depending on your project, you may want to attach to the nose cone slightly differently, but this is a good generic method I've found for lightweight nose cones. And just puts a post in place and you can tie the shock cord and parachute around that. But again, this is your model. You have access to the original, so create a copy and modify it as you choose. In my case, I've gone with 1/4 inch and I made that the same for both, so that gives me a round post to attach things to. But you can adjust them separately. Now looking at some of the calculated parameters, we've already seen some of them. So for example, the scale and the body length. But there are some others that are interesting as well, and it depends to a large degree on how you're building your model, whether or not these are required. So we have the leading edge and the trailing edge of the fin from the base of the rocket. The main reason you'd want to use this is if you're not using the fin can as a 3D printed model. So for example, you're making your fins out of balsa or out of birch for a high power rocket and want to do through the wall fins. This will give you the location of the leading and trailing edges from the base of the rocket so that you can cut your slots or just glue the fins into the correct position. The last one I advise you to use with caution. This is the center of pressure as specified on the diagram. It shows on the diagram as a subsonic center of pressure. In this case, I've measured it from the base because it's close to the base. I would take this one with a grain of salt. I would certainly want to do a simulation to make sure that this is correct, but it does give us a good idea, a second opinion on our simulations. So it'll help us validate our simulations. But again, don't rely on this one for your center of gravity and center of pressure calculations. Do your simulations, and that'll help you in other ways as well. Okay, so how does this work in the sketches? So if I go down to just the basics of the nose cone without the details, okay, you can see that the dimensions are constrained using these fx's, and that means we use a calculation. Okay, so for this particular dimension, it's 25 inches in the diagram, divided by scale, and again times 1 inch to ensure that the dimension is in inches and not the default of millimeters used inside the product. It added a second one because it just does that. That's one of the quirks of Fusion. It doesn't hurt. It's not a big deal. Now, as we go ahead and modify this, so let's go back to our change parameters again. Let's set our outer dimension to 2 inches. Okay, and you can see it adjusted everything. So instead of about 1.7, we're now up to a 3 inch for this dimension. Okay, so this is how the parametric modeling helps us adjust for the size of our rocket. And you can see that that is done through the whole rocket. Not all the dimensions need the scale. For example, the, that one does, bad example. Let's look at the outer dimension. Yeah, it's just the outer divided by 2 because it's the radius and not the diameter. Okay, so let's put it back to where it was and bring on the full rocket. So how do we turn this into an actual flying model? Well, in terms of 3D printing, there's only 2 parts to print. There's the nose and the fin can. So let's get rid of the body tube. So you would select the nose, right click, save as STL, bring it into your slicer and print it as you normally would. Now this is a pretty long object. In my case, I can print it vertically because my printer is big enough at this scale, but my old printer, for example, is not. So you may need to do it a little more horizontally. If you're going to do that, you're going to want to print it in a very fine detail. Otherwise, you're going to get a lot of print artifacts along the length of the nose. The other option is to split this up into pieces. I don't do that for this particular project, but I'll show that in later videos how we can do that as well. It's something I've done with my Saturn V and with my Saturn 1B. Okay, so we printed out the 2 pieces in 3D printing. Cut our body tube to length. We glue the fin can onto the body tube. In my case, I just use basic CA glue for that. There are some pieces we need to add. We need to add a motor mount. The motor size depends on your project. For this particular one, I've chosen an 18mm motor mount. It's a nice, inexpensive motor to fly, so A, B's, and C's. And that had just the regular retaining hook and the normal pieces you would have to find in a motor mount. The launch lugs is one area where you need to be careful. the diameter of the nose cone is actually larger than the diameter of the body tube. So you're going to need a standoff of some sort. So you do want to see what the outer diameter of your nose cone is versus the body tube. In my case, it was about 2 millimeters, so I created a 3 millimeter standoff with some scrap balsa that I have for another night smoke that I'm building. So again, be aware of that. For the shock cord and parachute, I used a standard length of Kevlar for the shock cord, a standard attachment method. Remember, when you're attaching this to the body tube, to leave clearance for the nose cone so you don't get stuck halfway. The parachute for this one, at this scale, I used I will be using a 15-inch. I don't have one currently, it's on order. I have some 18 inches, but that would allow the rocket to be carried a long, long ways, and I'm too old to be chasing rockets when I don't have to. So I'll be waiting for the 15-inch. You're going to want to paint and prep the way you normally would. It's towards the end of painting season here. I live in Canada, so our season's a little shorter. It'll probably be this spring before I get it painted, but it'll be next summer before I can fly it anyway. So I have a lot of time to build things, and I can paint it all at once. The last thing you need to do, and the first thing you need to do before you fly, is check your center of gravity and center of pressure to make sure things are stable. So in an upcoming video, I haven't done it here, but I will be walking through simulating a Nike smoke using OpenRocket and RockSim. And that will allow us to verify stability. It will allow us to select the appropriate motor and so on. But that'll be a forthcoming video. Do not fly without simming. Even if you're flying this model, I have not checked my balances at this point. I'm pretty sure it's going to be fine, but I need to verify. And you'll also notice I don't have any motor recommendations. So that's it. With this basic model, we are going to be able to build this rocket in a variety of formats and sizes. I'm probably not going to be using the Fusion 360 version. I've also developed a FreeCAD version, which is the subject of an upcoming video as well. And that's the one that I'll be using primarily to adjust sizes for different projects. But that's it. Go ahead, build, have fun. Show me your models if you build it, and I can be contacted in a variety of ways, either through the Rocketry Forum here on YouTube or on Twitter. But yeah, send me pictures of your builds. I'd love to see them. Have fun flying.